When you think of a black hole, an image of a cosmic monster immediately comes to mind, a creature that devours everything in its path, including light itself, from it. There is no escape. It symbolizes the end, the death of a star, the universe's ultimate point of no return. For decades, the black hole was the very definition of destruction. But here lies the paradox: the black hole, long seen as the end of everything, might just be the key to humanity's future survival. New research reveals that black holes don't just take, they can also give. Black holes could be a source of infinite energy and a gateway to traveling faster than light, not by breaking the laws of physics, but by harnessing the very way the universe works.
How does the energy get out? Which way does it go? It's not going to exit through the accretion disk because the accretion disk is in the way. How's it going to get out? Oh, wait a minute. If it's a disk and I'm energy and I want to get out and I can't get out through the disk, I want to get out above and below. So when we look at the anatomy of black holes, we find accretion disks and plumes of energy.
The story you are about to hear will completely flip that perspective. We will journey from the true nature of black holes to the strange structure within them, and then explore a region where energy can literally be extracted. And finally, we will ask a critical question. Could this monster become the engine of humanity's future? First, what is a black hole? In its simplest form, a black hole is a region of space where gravity is so strong that nothing, not even light, can escape. This isn't because it sucks light in like a giant vacuum cleaner, but because it warps space-time, the very fabric from which the universe is woven. Imagine space-time as a stretched, flat sheet. A heavy ball placed on it will create a dent. The heavier the ball, the deeper the dent. Now, if you take an object with immense mass and compress it into a small enough space, the fabric will be torn through, and that is a black hole. The boundary around a black hole, beyond which light cannot escape, is called the event horizon. It is the point of no return. Once you cross it, all paths lead to the center. There's no invisible wall there, but if you step across, you are never coming back. As terrifying as it sounds, this concept is perfectly understandable with conventional physics. The event horizon isn't a magic door, it's simply a speed limit to get out from within it. You would need to travel faster than light, something forbidden by all known theories. What's fascinating is that from the outside, we can only know three basic things about any black hole: its mass, its spin, and its electric charge. It's like describing a perfect sphere with just three parameters. Physicists call this the no-hair theorem, meaning a black hole reveals nothing else about its past, whether it was formed from a star or a cloud of cosmic dust. If the mass and spin are the same, it looks identical from the outside. Based on mass, black holes are divided into several types. Stellar mass black holes are the smallest, born when massive stars explode in a supernova. Larger, rarer, and more mysterious are intermediate mass black holes. And at the center of galaxies are the true giants, supermassive black holes, weighing millions or even billions of times more than our sun. Our own Milky Way has one such monster, Sagittarius A. Though we can't see black holes directly, we can detect the footprints they leave behind. As matter falls in, it doesn't go straight down but is pulled into a swirling accretion disk. There, gas and dust collide, generating friction and heating up to millions of degrees. They blaze brightly in X-rays and gamma rays, a brilliant flash of light just before the matter disappears forever. If you were to look with your naked eye, you wouldn't see the black hole itself, but you would see a blazing ring of fire swirling around a dark abyss. This is the black hole shadow that the Event Horizon Telescope famously captured. In short, a black hole is not just a hole in space, it is the most extreme consequence of gravity. A place where time and space are bent to their absolute limit. And it is at this limit where light breaks and matter vanishes that the most important clues about how the universe works are hidden. As you get closer to a black hole, gravity intensifies to an unimaginable degree. Once you cross the event horizon, all paths point only toward the center, to you. Everything might seem normal, but to an outside observer, you would appear frozen at the edge. Your time slowing to an infinite crawl, the light from you redshifting until it vanishes completely. At the heart of a black hole lies the singularity, a point where matter is compressed so densely that space-time is infinitely curved. In other words, this is the dead end of physics. All of Einstein's familiar equations break down. We cannot describe what happens there, only that the laws of nature as we know them cease to function. If the black hole isn't spinning, the singularity is a single point. But if it spins, it becomes a tiny ring, a structure that makes the surrounding space incredibly complex. Some theories suggest that passing through this ring could lead to another region of spacetime, what science calls a wormhole. However, there is no evidence that anything could survive the journey. In reality, falling into a black hole is nothing like the movies. There's no explosion or impact. You would be silently stretched apart by tidal forces. The part of your body closer to the black hole is pulled much more strongly than the part farther away. As a result, you are drawn out like a strand of spaghetti, a phenomenon scientists amusingly call spaghettification. In a small black hole, you'd be torn apart before even reaching the event horizon. But with a supermassive black hole, the gravitational forces are more evenly distributed, allowing you to cross the boundary without even noticing. Still, sooner or later, you are pulled to the center where both space and time end. It sounds like the ultimate end. But strangely, the most interesting phenomena aren't at the center, but on the outskirts of the black hole where space-time begins to twist like a giant vortex. Most black holes spin incredibly fast. When a massive object spins, it doesn't just pull matter along with it, it drags space-time itself. This phenomenon is called frame dragging. You can imagine stirring a cup of coffee. The liquid near the spoon swirls with it, while the liquid farther out moves slower. The space around a spinning black hole gets twisted in exactly the same way, except the liquid here is the very structure of the universe. The region where this effect is strongest is called the ergosphere. It lies just outside the event horizon and is a place where everything, even light, is forced to rotate with the black hole. However, unlike the event horizon, you can still escape the ergosphere if you move in the right direction. And it is this very region where physics offers us a gift: energy. In 1969, physicist Roger Penrose realized the ergosphere could act as a colossal cosmic turbine. He proposed a thought experiment, later called the Penrose process. If you send an object into the ergosphere and split it in two, letting one piece fall into the black hole while the other escapes, the escaping piece can emerge with more energy than the original object had. That extra energy comes directly from the black hole's rotational energy. In other words, Penrose found a way to borrow energy from an object thought only to devour. If applied perfectly, humans could extract up to 20% of an object's mass as pure energy, a process dozens of times more efficient than nuclear fusion. It may sound like science fiction, but the universe has been doing this for a long time. The relativistic jets stretching thousands of light years from the centers of galaxies are the most vivid examples. They are created when magnetic fields and matter in the ergosphere are twisted, launching enormous amounts of energy out into space. This means that even in what seems like a pit of death, the universe is creating life and energy. Black holes don't just consume everything, they also operate the most powerful natural generators we have ever known. For centuries, black holes existed only on paper. The idea was so radical that even Einstein, who predicted them, doubted their existence. But the 21st century proved him wrong. Black holes aren't just theory, we can actually see and hear them. In 2019, the world was stunned when the international team of scientists at the Event Horizon Telescope, EHT, released the first ever image of a real black hole. Not an illustration, not a simulation, but actual light, collected from dozens of telescopes spanning the globe, linked together to form a single virtual telescope the size of our planet. The result was an image of M87 Planck, the supermassive black hole at the center of the Messier 87 galaxy, 55 million light-years away. In the photo, a brilliant ring of light surrounds a dark core, the black hole shadow. The light doesn't come from the black hole itself, but from its accretion disk, the hot gas and plasma swirling around it. This ring is bent by gravity, creating the image of a great ring of fire, exactly as Einstein's theories had predicted over a century earlier. 3 years later, in 2022, the EHT followed up with an image of Sagittarius A, the supermassive black hole at the center of our Milky Way. It is thousands of times smaller than M87 Tel, but much closer, only about 26,000 light-years from Earth, though smaller and more volatile. Its image revealed the same ring-like structure, proof that all black holes, big or small, obey the same cosmic laws. If the EHT let us see black holes, another project allowed us to hear them. In 2015, the LIGO Observatory detected the first gravitational waves in history, real ripples in spacetime, created when two black holes collided and merged. That signal, designated GW150914, lasted less than a second, but contained the energy equivalent of 3 suns exploding. When converted to sound, it's just a tiny chirp, but it is the authentic sound of the cosmos. For the first time, humanity heard the echo of spacetime itself. From that moment on, black holes were no longer abstract. They became real objects of observation both for our eyes and our ears. The combination of the EHT and LIGO has opened a new era, multi-messenger astronomy, where we don't just look at light, but we also listen to the heartbeat of the universe. Every new image, every new gravitational wave signal tells a story of how the universe works, collides, and is reborn. Once just dark voids, black holes have now become beacons, illuminating humanity's understanding of the cosmos. When we look at the big picture, a black hole is not just a point of death, it is the engine that drives galaxies. At the heart of most galaxies lies a supermassive black hole. As they feed, they blast out enormous jets of energy, creating active galactic nuclei, dazzlingly bright regions that can sometimes outshine their entire host galaxy. This power plays a regulatory role. When a black hole ejects energy, it blows away gas clouds within the galaxy, preventing them from collapsing to form new stars. This keeps the galaxy in balance, preventing it from growing too quickly. Without a central black hole, star formation could run out of control. Those same jets also spread heavy elements throughout the universe: iron, carbon, oxygen. The very elements that make up planets and life were seeded by the winds of ancient black holes. Whether by accident or design, they helped create us. Therefore, calling black holes destroyers is no longer accurate. They are cosmic architects simultaneously destroying and creating, consuming and nurturing. If one day we truly understand how black holes bend spacetime, perhaps we could do the same. Not by exceeding the speed of light, but by warping the fabric of spacetime itself, letting it carry us faster. This is the principle behind ideas like the warp. Drive a vehicle that moves by bending space around it. Black holes are the perfect natural laboratory for this idea. Their ergospheres show us that if we learn how to ride spacetime, we can move faster than light without ever violating Einstein's laws. That day may be far off, but every new picture we take, every new gravitational wave we record, is another step toward understanding the true language of the universe, the language of spacetime. The black hole is the universe's beautiful paradox. It swallows light, yet creates the most brilliant rings of fire. It destroys, yet it also builds. It is the end of a star, but the beginning of new questions. Perhaps one day, humanity will no longer fear black holes, but will learn to use them just as we once harnessed fire, electricity, and the atom. Because within nature's most terrifying creations, there always lies a great potential if only we are curious enough to get closer. And if there is one lesson a black hole teaches us, it is this: do not be afraid of the dark, because in the darkness, there is always something worth discovering. If you want to continue exploring the unsolved mysteries of black holes, please like, subscribe, and join me on this journey to the cosmos, where everything that seems impossible might just be within our reach.